Hi everybody. So today we are going to look at chapter 3, image restoration. So I'm going to look at what we are going to look at. Like for example, we are going to do how to restore image that has been degraded with noise. So for example, where we have noise like this, a salt noise or pepper noise or both salt and pepper noise. And we also look at how we could restore image that is degraded with Gaussian noise. Okay, so that's first type. And then we are also going to look at how we could restore image that has been blurred. So image that is blurring. Yeah. Okay. Image that has been blurred. So how do we restore them into something like this? By using frequency filter. And we also will look at how to restore image that has been degraded with interfering noise like this by using what we call a notch filter. And we also look at how we could restore image that has been geometrically distorted like this. So we try to restore back to something like this. So if you look at image restoration, in bahasa Melayu we call it baik pulih. So when we say we pulihkan means try to put it back to the original condition. All right. So so the basic concept here is when we have some degradation, like for example in this case, the degraded image is actually the original image plus with some noise. So what we can do is we try to do the inverse of the degradation process. So that is the core idea of restoration. So you need to know what caused the degradation, and then you apply the inverse, okay, of it. So if the degradation is positive at, then to restore we minus n. So if you look at the general flow chart of this, so basically you have a degraded image and also the knowledge of the degradation process. So you develop the degradation model, and then you develop the inverse of that. Just like here, the degradation is plus. So to restore, you apply the inverse, which is minus. So you develop the inverse, and then you apply the inverse to the input image, which has been degraded, and then you get your output image, which has been restored. So that is the basic idea of image restoration. So next, I'm going into this frequency filter. I'll jump a little bit spatial filters, because this frequency filters is a very good example of applying inverse. So we look at this inverse filter. So in this inverse filter, we model the degradation as blurring or smoothen image. So in this case, what we want to do is we want to restore a blur image like this from here to here. So we start to do the modeling. So the modeling is actually how do we get this degraded image, the blur image, from the original image. So we know that when we do convolutions with all positive mass, then we tend to get a blurring image. So we model the degrading image as the result of original image, convolve, this is convolution, all right. So with the blurring mask. So that is our modeling process. And usually there is noise, but to make it simple, we assume there is no noise. All right. So so we begin from here. So if you look at this convolution, the problem to restore by using convolution is there is no direct inverse. All right. So we have to go around this by making use this very famous convolution theorem, which you might not have heard before. Convolution theorem actually tell us that convolution in spatial domain is equivalent to multiplication in frequency domain. So since convolution has no direct inverse, so we try to do things in frequency domain, because in frequency domain it is convolution is equivalent to multiplication in frequency domain. And when it comes to multiplication, then there is a simple direct inverse, that is division. So with that, then we are ready to go. All right. So we use the model from here. So we do transform to frequency domain. So instead of RC, now you can see now the indexing is a frequency indexing, U and V. All right. So the D, after you transform to frequency domain, we get the UV, and now the equations, okay, become something like this. So at remains at, but the convolution now has become a simple multiplication. And with this simple multiplication, then we are ready to do the restoration. That is by apply the inverse. So now if you want to get I, very simple, you just get the D, and then you divide with H, like here. All right. So because previously you get D, you take H multiply with I in frequency domain. Now you take the degraded image, divide by the blurring mask. But of course, all this in frequency domain. Right. That's why we call this inverse filter. That is, we take the image in frequency domain, we divide with the blurring mask. So, but this is not the end yet, because this is still in frequency domain. If you notice the index UV, so in order to get the image, restore image in spatial domain, so we have to do inverse Fourier transform. So F -1 here means inverse Fourier transform. So you inverse Fourier transform the image, degraded image divided by the blurring mask. Okay. So so note that the inversion is a point-by-point inversion, not matrix division. Okay, it's a point-to-point division. So you divide. Okay. So to show you how this thing works in MATLAB, so you can go to the lab manual 08, lab 08, and then you double-click this inverse filter. Okay, so I'll show you the code. So this codes, you can see that I take the original image and then I try to add with some noise. Okay. Sorry, not add with some noise. I'll try to create a blurring mask, Gaussian blurring mask. So if you look at I try to run this. Okay, take a little bit of time. So this is my blurring mask, H15 by 15. We look at it all positive, and it's actually only the center is non-zero. Those that is near to the side, it's basically close to zero. All right, so if you look at this is the original image, and this is the blurring mask, and this is what you get if you do convolution between image and also a blurring mask where all positive like this. And you can see that the image has been blurred. And I'm going to show you how I'm going to restore to this. That is, I transform this into DUV, and I transform this to HUV, and I take DUV divided by HUV, which I do it here. Right? Then I do the inverse. So this is my restored image, which I display here. So you can see that, now the image becomes sharper like the original. So if you look at the spectrum here, actually after blurring, you can see that the high frequency, this is the lowest frequency. And as you go the higher and higher frequency, so the high frequency become very dark, meaning that the high frequency magnitude has been reduced as compared to the original. Actually, the high frequency magnitude is not as low as compared to the blurred image. Okay, if you look at this, actually what happened when you do blurring is you're taking this and multiply with this, and this blurring mask, if you look at the frequency, the spectrum of it, the low frequency is very high, and then the high frequency, the magnitude is very low. So when you multiply, you're practically removing the high frequency, making the image blur. Okay, and then when we do divisions, so you'll find that this is what happened. All right, when you do multiply, you actually duck out the high frequency region, so you're making them the high frequency less, so the image become blur. So when you divide, so what you get is now you divide all the high frequency with small value. So practically you are actually increasing them back. All right. And then after restored, you get the restored image, which is much sharper. So that is basically what is inverse filter all about. All right. So, okay, in the exam, basically you are only asked, let's look at some of the sample questions. Let's check on the your sample question, which is in your additional notes. We'll look at the sample questions. Okay, not much calculation. Basically, it's okay. Spatial filter 29, which 29. All right. So image like this, where we are asked to propose a mathematical equation suitable to model the degradation process. If you look at the degradation process, this is basically blurring. Okay, so so blurring you can model as convolution. So it's basically original image convolved with the blurring mask HRC. And then if you look at convolution theorem, so in frequency domain, convolution is equivalent to multiplication. And in order to get your restored image, IUV, so you take DUV divided by HUV. So the general steps then become something like this. So you need to have your HRC, you can estimate that. And then you transform both HRC, DRC into frequency domain so that you get HUV and DUV. And then you compute DUV divided by HUV, which will then give you IUV. So all this actually comes from the model here. And then to get IRC, you have to inverse transform IUV so that you get IRC, which is the restored image. Okay, like here. So transform both, divide, and then inverse. Then you get the restored image. All right. So that's basically about inverse filter. Okay, so that is all about inverse filter. Let's move on to another frequency filter, which is a notch filter. Actually, there's many more inverse filter, but I'm not going to talk about that. But instead, I'll go into notch filter. So notch filter is some kind of a band reject notch up. So if you look at this image here, a normal image, usually they will have behavior where the lowest frequency tends to have very bright, means very high intensity. And as you go out, all these are actually higher frequency, so their intensity tends to be lower and lower. But if you have abnormal image like this, then you will find that in this high frequency region, okay, it tends to have very high intensity, which is abnormal. So in order to remove the problem, so it's quite difficult to do it in spatial filter, but the problem is very easily identified in frequency domain. All right, so then you can see all this extraordinary high peak here, the very high bright dot. So this is the problem. So it's not supposed to be that high. So in order to restore, what you need is just to make this to 0. Okay, very simple. So extraordinary high, we make it to 0. And then you inverse, then you'll get image without the interference. All right. And usually you will lose some contrast, so you can do IM adjust or contrast enhancement, then you get the image. So this is a notch filter, and yeah, it might be it's also asked in the exam. Notch filter, something like this. So you'll be asked to restore, remove the artifacts, figure 11, figure 12. So then what you need is basically to explain the steps. All right, so the high frequency pattern here, the stripes is basically high frequency pattern. So they will appear as high peak in high frequency region, like this. Sorry. Okay, so it appears to be in a high frequency region, like this. So then in order to remove that, so you remove the high peak that is here. You remove these two bright dots in the high frequency region with extraordinary, abnormally high. So you remove them, set to 0. So that's why now you see two dark dots here, because we already set to 0, or set to any value close to their neighboring values. So the step will be you have to transform the frequency domain. So transform frequency domain, and then identify coefficient with high frequencies and with abnormally high magnitude, much higher compared to the coefficient. So this is high frequency region here, okay, and then you can see this very bright compared to the surrounding, means they are the abnormally high magnitude. So this two is the one that contribute to this. So what you need to do is set them to 0 and then inverse transform. So set to 0 and then inverse transform, we should get something like this. So that's basically how you try to perform notch filter. All right. Okay. So this is about frequency filter. All right. So you see how we apply the concept of inverse. And for spatial filters, okay. So spatial filters, basically we try to remove two types of noise. The first type is called the speckle, where you have image where you have something like this. We go to sample image, where you have things like salt and pepper noise, where it is a kind of sudden height or sudden dip. Okay, salt pepper noise, very bright or very dark compared to surrounding. So this type of noise usually is good. It's easy to remove if we use the order filter. So order filter is something like median filter, where you have to order them, sort them, and then you choose either the middle, that's median filter, or actually you can also choose maximum, so that's the largest or the smallest, depending on what you want to remove. But usually we just do both. We select median, and that will be effective to remove salt and pepper noise at the same time. All right, so this is the result. And you can see that if you use a bigger mask, then you tend to have this kind of posterization effect. And then we have another type of noise, we call them Gaussian noise or uniform noise, where it's a small fluctuation, okay? It's not a sudden high or deep like pepper or salt noise. Okay, but I hope you can see their difference. Okay, so it's a small fluctuation. So this is called Gaussian noise. So to remove Gaussian noise, so what we do is we do mean filter, where you apply a convolution mask with all positive. So you calculate the average. All right. So when you calculate the average, then you tend to remove noise, flattening the things. Okay. So and if you increase the mask size, this is 3 by 3, and this is 5 by 5. You can remove the noise better, but at the same time, you will blur the image. So this is actually a problem, which will bring us to another filter called adaptive filter, which is much more. Okay, I'll show you the results of. Call it minimum mean. So this is the. If you look at these results here, all right, this one. So this is called minimum mean square error filter. So you can remove the noise, but at the same time you don't blur it. Okay. So I'm going to use this and show you, compare with the results of mean filter 9 by 9. So you can see that obviously this is much better compared to this. So how do we actually perform this? So this is called adaptive filter. So adaptive filter means you try to be filter according to the subregion, the characteristic of subregion. So you can become adaptive to the subregion. All right. So you don't filter equally throughout the image. So you try to be adaptive. That is, you only target on certain areas. So how do we actually perform adaptive filter? So I'll give you a hint. If you look at this, you can see that actually near the edge, there is still noise. So they actually do not perform any filtering near the edge and details, because that's the purpose. We do not want to blur the edge and details like what the mean filter do. But when it comes to a flat region like this, okay, flat region like this, where we know that there is no details, so only noise, then we can do mean filter thoroughly. So that's why in this kind of region with constant value, so we will be able to remove noise effectively, but we do not do any filtering in the edge. And this is actually done by using adaptive filter, or minimum mean square error filter. So you can look at this formula here. So DRC is the original pixels value. So we actually do a moving window operation, and then we actually guided by the local variance. Okay, the variance of the window of the sub image. Okay, and then minus with the mean of the window. Right. So if you look at this, what happened when there is no noise? Okay, let me open up this board. So let's analyze. So how this actually work. So this is the original equations of MMSE, where you take original image minus with this ratio multiply with the difference between original and the mean. Now, we have two cases, two scenarios where we have regions without edge and details, like this one, this region here. Okay. So when it comes to region without edge details, so you'll find that the local variance and the noise variance is very much similar, because there is no edge. Because edge usually, if you look at edge, they have very large difference. So the variance is much large. But in this area, the variance tends to be almost near to noise variance. So then you will find that the local variance is close to noise variance. And then if both actually very close, then it's almost equal to 1. And therefore, this equation will become something like this. And you'll find that eventually, if you simple up, okay, then this will minus the RC, cancel out each other, minus minus positive. So you get, actually, this MMSC will basically comes to calculating the mean of that region. So this is practically 100% mean filter. And when come to region with edge and details like here, okay, so then you'll find that local variance is actually the variance of edge and details plus noise. So noise will give you the variance, but the bigger variances come from the edge or the details. So then you will find that the local variance is much greater than noise variance, and then this ratio will be close to 0 because the denominator is much greater. All right, and this whole thing, you see, when this ratio becomes 0, this whole thing cancels out. So left only the RC, which is the original pixel value. Or in other words, now MMSC return the value with no filter. So you can see that now when there is no edge details, we perform 100% mean filter. And when there is edge details, we don't do any filter. And that is the reason why you have something like this. Those were flat area, we do a lot of filtering, so no noise. And those area with edge, you don't do any filtering, although there's noise, but you preserve the edge well, and eventually you get a much better, clearer image. So that's basically MMSE. So if we look at the questions. Okay, so we look at these questions first. Okay, so the questions ask you to perform arithmetic mean filter. So this mean filter very simple. So basically you just, in this case, mask size 3, so you just 3 by 3, and then you calculate the average. So if you calculate the average, then you get 117. So that is the new pixel value. Instead of 50, now become 117. And then for second, then you go for the second mask, second window. So you calculate the average of this window, and you get 183. So that is basically the conventional arithmetic mean filter. And then this filter works well to reduce, but has an undesired effect. What is the effect? So the effect is it can cause blurring. Okay, so how would this undesired effect change if you use much larger and larger? So if you use larger mask, then the blurring effect will become worse. All right. Okay, so the undesired effect you have stated happens because arithmetic mean filter applies the same amount of filtering to all parts. So to get better result, you should given different amount of filtering. So ideally, how much filtering should be applied to the parts where contain constant value. So when there's constant value, no edge, then you can apply as much as possible, 100% mean filter. And for the parts where contain edge, then you don't do any filterings. So that is what we want to achieve in adaptive filtering. So we filter according to the conditions of the sub-image. All right. Here's another questions. You're given image O, original with noise. So then you try to do some mean filter. So I'll try to do some mean filter, and you get this one, P. So, but still noise, so not happy. So he adjusts some parameter to perform, and he get another result. So do you know what parameter he adjusts? Yes, you can see that now he can remove more noise, but image become more blur. So he actually use a bigger mask. So you increase the mask size, so then you get a more smoothing effect, but at the same time you actually blur the image. So X, actually you get it from adaptive. So do you think Ahmad will eventually get a satisfactory results by merely adjusting the parameter? So obviously the answer is no, because if you use small window size, then you can remove noise. effectively, but if you increase the window size, then you tend to blur the details of image. This is what happened. Small window, yes, you can't remove noise very well, but here you can increase window size, you could remove the noise well, but the image become blur. Okay, so this is MMSE. So this equation. So MMSE is an example of adaptive filter. So describe the meaning of adaptive in the context of filtering. Right. So adaptive means the characteristic of filter change according to the characteristic of sub-image. So that's adaptive filter. So based on this, briefly describe how adaptive filtering is accomplished. So if you refer to that, so when there is H, then this noise variance was much smaller compared to local variance. Then this become original image. So returns original pixel value, no filter. And when there is no H, then noise variance similar to local variance. Then this will become like what I have shown you. So then MMSE return the mean of window. Okay, and in other words, it perform the mean filter to the fullest. All right. So that's practically okay. Now I also want to show you. I prepared the MMSE code here. You can take a look. So what we do here is if you run. So basically, you crop up the image, asking you to crop estimate noise variance. So you try to crop those regions where in the sky where there's no edge, no details, only noise, so that we know roughly what is the noise variance. So then I apply the sliding window operation according to the equations. You can check here. Okay, the original image minus this multiply with the mean. Okay, so this is the equation. Okay, so take a little bit of time. Again, this is under lab manual lab 08. So you can look at the image, original, noisy. This is what you get if you use mean filter, and this is what you get if you use MMSE. And if you try to enlarge, you can see that the difference is actually, see, the edge, we don't do any filtering. We only filter those area without edge. And that's where we actually maintain the original image, the object very well. Okay, so basically that is what I want to share with you. Thank you.